Okay, so let's continue exploring the electric field that we get from multiple particles, and then imagine placing a third charged particle in the xy plane and evaluating the electric force on that third particle. So here is our xy plane. Okay, so let's choose a particle of charge. Let's put a particle of charge, say Q naught. Actually, let's make it negative. Minus Q naught. And its location is x equals a, y equals 0. And let's put another particle of the same charge. It's also negative. Minus Q naught. At the origin, x equals 0, y equals 0. And let's evaluate the electric field created in the xy plane, and then we'll put another particle in the xy plane, and we'll consider the electric force on that particle. So the electric field that's created in the xy plane as a result of these two particles is just the sum of the individual fields. So this particle creates an electric field which is minus k times q naught, because the particle has negative charge, times x, it's the x value of the location where we want to evaluate the field, minus the x value of the particle that creates the field, and we're considering the field produced by this particle, so we have x minus a. A is some positive number. I hat plus y minus y naught, but the y naught is 0, so we have y j hat over x minus a squared plus y squared all to the 3 halves, again because of the unit vector and the r squared in the denominator. To this I'm going to add the electric field produced by this particle. So I have minus k q naught, because that particle has negative charge as well, times I have x minus the x coordinate of this particle, which is 0, so I have x I hat plus y minus the y coordinate of this particle, and that's 0 as well, so I get x I hat plus y j hat and that gets divided by x squared plus y squared to the 3 halves. Okay, so that's the electric field at any location in the xy plane. So if I choose, for example, x equals minus 10, y equals 10. So somewhere over here, I'm going to put in values of 10 for x, here, here, here. Sorry, minus 10 for x, and 10 for y, and I'll get the electric field over here. And now I can sort of tell that the electric field here, say right there, due to this particle, will be pointing toward that particle, so that way. And the electric field due to this particle will be pointing toward that particle. So I'll have two vectors pointing this way, and then the resulting vector is the sum. It'll be somewhere in between, pointing that way. Okay, so I could choose to place the particle, the third particle, anywhere I want and get an expression for the force. So let's say we have a particle of charge Q1. Okay, so positively charged particle of charge Q1. And so we go from electric field to electric force, and we just have to multiply Q1 times the electric field that it's in. And the electric field that it's in is this. So the force on the particle of charge Q1 has two terms. It's just minus K, Q naught Q1 times X minus A. Okay, so this is the force on this particle of charge Q1 at an unspecified location in the xy plane. So x and y are left unspecified, minus K Q naught Q1 times, we don't actually need square parentheses here, plus y j hat Okay, so that's the force. And what we can do is to get a sense of what we would get if we placed this particle of charge Q1 at a specific location. Let's place it somewhere where we have a sense of what we'll get. So if we put the charged particle right in between here, so here is particle of charge Q1, and it's at A over 2. So the force due to this particle will be that way. The force is attractive, but the force due to this one will be that way, and they will be equal in magnitude, and so the net force would have to be 0. So let's make sure that in fact we get that. So the electric force on the particle of charge Q1 located at x equals A over 2, y equals 0 should be 0. Let's see that that's in fact the case. So what does this expression reduce to? We get minus K, Q naught Q1 times x is A over 2, so we get A over 2 minus A. That's minus A over 2 I hat. Y is 0, so that goes away, over A over 2 minus A, that's A over 2 squared, so that's A squared over 4. And here we have minus K Q naught Q1 times x, which is A over 2, I hat, plus 0 here, divided by A over 2 squared, so that's A squared over 4 plus 0. Oops, sorry, I forgot the 3 halves in both cases. So here we have this to the 3 halves, and here we have the same thing. And we can see that, let's just write one more line here. Actually, let's come over here. So actually, let's come up to here and say the force is therefore equal to, right, we can simplify this. We get a positive value here. We get K Q naught Q1 A I hat over 2, right, so this 2 I brought into the denominator, and then we get, we have an A squared to the 3 halves. That's the same thing as A cubed, so I get an A cubed, and I have the 4 to the 3 halves. That's 2 squared, so that's really 2 to the 3rd, but in the numerator. So that's 2 times 2 is 4, 4 times 2 is 8, so I have a factor of 8 here, and I can simplify. And here I have the same thing, but with a negative sign, so I get K Q naught Q1 A I hat over I'll do the same thing I did here. So I'm going to take the 2 and put it down in the denominator. I have the a squared to the 3 halves. That gives me an a cubed. And I have the 4 to the 3 halves. That ends up, I have 1 over 4 to the 3 halves. So that ends up in the numerator. So I have the 8 here. And that becomes a 4. But these terms are the same. So in fact, they cancel out. And we get what we expected. That the force, the net force on the particle here, is 0.